Welcome everyone. My name is Gerardo Ochoa. I'm a technical sales engineer, part of the Simolia structures team at Bios 3D. My experience is I've been working on different FEA applications for the last 15 years. Some of this time I spent working on injection molding applications as well as structural simulations. I've been with Bios for the last 5 years, and my main activities are working on deploying and modernizing simulation workflows with our customers using the MODSIM approach. So for today, we're going to be talking first about MODSIM. I think it's important to define what is it, and then how this MODSIM approach could be applied to different simulation workflows that are intended for plastic components. We're going to start with injection molding simulation. This is important because this is the simulation where we're going to get the input we need for this type of applications. And then the focus will be more on the mapping the fiber orientations, doing some out of the mold warpage. We will also talk about warp compensation for injection molds, and then very important to discuss about the automated design exploration using the MODSIM approach. So to start with MODSIM and defining what is it exactly, if we have to use a phrase, we can say MODSIM is unifying modeling and simulation using a common data model within a single user experience, and we're using 3DEXPERIENCE platform as the main driver to allow these workflows to happen. The platform is basically the environment that unifies all the Dassault Systems technologies that can make all these automated workflows happen seamlessly. Now, MODSIM is not exactly a software or application or a product by itself. MODSIM is more like a process transformation. So if we consider the traditional simulation workflow between design and simulation, the traditional approach is we get the design CAD data from we could get the geometries from an email or a share folder or FTP location. Then we grab the CAD model. Many times we have to perform some geometry cleanup operations, and then we start with meshing. Then we define our simulation setup. We execute the job, and then we evaluate the results. And when we get the results, we start evaluating the scenario, and based on the output, we define if we can go back to the CAD design and perform modifications and start the same workflow again. That's how the iterative process works. So everything is based on files. And what's different with MODSIM, and I'm going to be illustrating this in the upcoming slides, but basically with MODSIM, we're using the 3DEXPERIENCE platform as the enabler to connect all these steps during the workflow. As I said previously, using a common data model, that is, all the users involved in this workflow are going to be using the same data. We're not talking about files, we're talking about data. So this allows for full associativity between all the information we need to manage to execute this type of workflows. And by this, since all the data is connected, if we perform a modification in the design, that modification will be automatically propagated through the entire or dependent other steps, like, as we said previously, geometry cleanup, meshing, scenario definition. Now, how the MODSIM technology works. So if we start with the modeling side of things, there are some steps that happen on that side. We can start with if we're talking about the entire product, we may start defining the product architecture. We can also work on, some uh, concepts, and then we define the product, and then we have the initial 3D design of that particular product. What we're looking at here is uh, from the assembly level on the 3D experience context. This is we call it the physical product, and then inside the assembly we have 3D parts, and then the 3D part is the physical representation of a component. So that physical component could have multiple representations, and that could be a shape, that could also be the material definition, and for the shape, we can also have some features inside these representations. And those could be model parameters or features such as, uh, trading solids. So that's from the modeling side of things. Now, this is where the simulation intersects. So if we take the previous three, right, in a simulation workflow, we pick a CAD design. That's what I was mentioning earlier about the traditional approach. We may get this from a email or share folder. Here is happening entirely on the 3D Experience database. So we pick a CAD, we start working on the geometry cleanup, and during this step, we create another uh, representation of the 3D part, and that's going to be an abstraction shape, which is, we can think about the abstraction shape as a copy of the shape, but where the simulation user can perform geometry cleanup tasks while maintaining a direct link between the original shape and the modified geometry. Same thing happened with the next step. We prepare the mesh, we clean up the mesh, and define connections, those kind of things. And the mesh is also connected to the abstraction shape, and at the same time, the abstraction shape uh, keeps being connected to the original shape. We do the same with connections in the structural simulation context. This could be bolted connections, connectors, welds, fasteners, all those kind of things. And then at this step, we already have our CAE model ready. And then we start with the scenario setup or simulation setup. And as we can see on the model tree, now we have at a higher model, the simulation object, which contains the initial model that's containing the entire assembly, and it's also connecting the scenario setup. So in the scenario setup, we define loads, boundary conditions, interactions, of all the features that are representing the scenario that we're trying to simulate. And then we execute the job, and then we get results. And in the same model tree, now we have the results attached. So that is, this will contain XY plots, sensors, custom calculations. All the post-processing tasks can be stored here. Then we have a CAE report, or the evaluation of the outputs. And then we start iterating again based on the outputs we are getting. So based on the output, the user may have to go back to the 3D design and perform modifications. And because of this connection between the 3D design and the simulation features, if we look at this model tree, these are connected. So the CAE model update will happen automatically. And this is not also for a single user. This could happen between different users. Let's say we have one designer, which is the user that will be performing the modifications. Then if the designer changes something, the simulation user on his workstation will see the the modifications propagated to the entire simulation model. So when that happens, the simulation user does not have to do something new. The environment will automatically update all the features such as the mesh or even the geometry cleanup operations. Those will be automatically applied to the modified 3D design. So this is what we call MODSIM, the MODSIM approach. So it's the data connected in the same environment for all the users. So there is no file exchange. There is no sending files from through email or FTP locations. Now, MODSIM has multiple layers. We're going to be focusing on the core MODSIM, which is just capturing, the design and simulation workflow. But there are other layers, such as validation and certifications or process automation, where since everything is already connected, we can automatically execute design exploration jobs. We can automatically match the simulation outputs. If we have experimental data, we can match the simulation with experimental data and perform validation and certification tasks. Requirements from a product could also be mapped to the simulation workflow, and as well as project management tasks, such as assigning tasks to users, deadlines, and share the simulation outputs to these tasks. That's also possible. But today, we're going to be focusing on the dark blue section of the entire MODSIM approach. So to show you one example how this works, I have this video. And in this video, we have a designer that has all the entire 3D model parameterized. There are different parameters being manipulated here. Some reefs on the near side of the model, reefs in the center side of the model. We have on the left side the model tree for the CAD design, and these are all the modules. And then this is passed to the simulation user. So the simulation user can automatically build different design options and then execute the job. And now the simulation user can see for all the different design variants, how each variant is, how's the response of each design variant. On the right side, we can see all the outputs that the simulation user is getting. So this is a brief example of how the MODSIM workflow is happening between a design user and a simulation user. And that was a structural simulation applications, but definitely there are different physics domain available to perform MODSIM workflows on the platform. We have electromagnetics, we have multi-body dynamics with rigid and flexible bodies. We have injection molding, we have a structural simulation, and CFD workflows. This is all the different physics domains available on the platform with the MODSIM approach. So now we can start with the injection molding topic. The important thing is to keep in mind the MODSIM approach, because the MODSIM approach is what is going to be allowing us to work seamlessly between the injection molding workflow and the structural simulation workflow. So starting with the injection molding, what I'm showing here in the entire slide is the whole workflow from designing the part to the mass production. So for today, we're going to be focusing on the part design side of things. That is, checking if the cavity will fill, require pressure, clamp force calculations, and other plastic part defects that could happen. This is the section of the workflow we're going to be focusing on regarding the MODSIM approach and how we can perform fiber orientation simulations. Going deep on the injection molding simulation workflow, what's available here is users can simulate the filling phase of the process in responses such as plastic pressure, temperature change, weld line predictions, air traps, all those kind of things related to the filling stage of injection molding process. On the other side, and this is going to be very relevant for the upcoming workflows, it's going to be the packing phase, where we are simulating the packing profile or the holding stage of the injection molding process. And this is going to tell us how the material is changing its density, and as well as how the temperature is changing to the point that the entire part is freezing. Then the same injection molding simulation environment could perform or can include some mold components such as the cooling lines or runner systems. And for cooling lines, this is used to calculate cycle times and heat exchange from the cavity throughout the mold. And also, it's possible to perform warpage simulation. For the warpage simulation, that's a very nice feature, because the warpage simulation, it's also nonlinear. That is, the warpage solver is not assuming any constant relationship between the deformation and the stresses we're getting. Actually, the solver behind the warpage step of this simulation workflow, it's Abacus, that is very well known for its linear capabilities. And here, I'm just showing a very brief list of different types of results, and I marked in red the relevant results we're going to be using for the fiber orientation workflow. So the filling analysis stage can provide the fiber orientation result that we're going to be using for structural simulations. The packing analysis phase can provide us the temperature time series to use the temperature as initial condition in the structural simulation. This is also very important if we're going to do or perform out of the mold warpage simulation using the structural simulation workflow. And then also very important, including the residual stresses from the manufacturing process. Just to mention, there is an active work between DS, R&D, and different material vendors. Right now, there are more than 4,000 different grades of materials available in the database. All users are always able to define their own custom materials and selecting different viscosity models, also different shrinkage models. For the injection molding simulation, users could also use the cloud for solving. They don't have to use their own machines to solve the simulation. Right now, with no extra cost, users can perform simulations on the cloud using up to 8 CPUs. And while the simulation is running on the cloud, users can also monitor some relevant outputs, such as the maximum injection pressure here. And just to let people know, after the simulation is run, if the simulation user needs to share results with other external stakeholders, the manager or some people from the shop floor, they can use the web browser to give them access to check some results. This is lightweight result visualization, and also automated reports can be generated. Now, that was the injection molding simulation side of things. That's the step that it's going to be giving us the input we need to perform structural simulations, considering the fiber orientation that's coming from the manufacturing process. Now we're going to start talking about the fiber orientation topic. Okay, so we're going to start talking about the challenge of designing fiber reinforced plastics. So we know this is considering short glass or carbon fibers. The material or matrix could be a thermoset or a thermoplastic resin. And the main goal of this is, increase from the structural side of things, the, the benefits are increasing the rigidity of the part, strength, and durability. There are of course, other benefits regarding the injection molding process. For now, we're focusing on the structural simulation side of things. Now, the material could also be complex, right? There is an heterogeneous part and an isotropic part. There is a lot of directionality in the plastic component because of the fiber orientation. There could also be some temperature dependency for the matrix and the inclusion, which is the fibers. Viscoelasticity could also be modeled for time-dependent material behavior. Also some plasticity, and if needed, damage and failure material models that are coming from Abacus could also be defined for the behavior of the plastic components. And there are also some effects at the microscopic level. We're going to be mapping the fiber orientation. We could also define the fiber shape, the aspect ratio, the volume fraction that represents the volume of the fibers, and as well as some weakness that we can define considering the weld line formation. This information is also coming from the injection molding simulation. And I will be also talking about the material calibrations, because if the user has experimental data, the experimental data could also be used to calibrate the material parameters for the fibers, or the entire, at the composite level. Now, there is a multi-scale material approach that it's the more classic, which is we're starting at the microscopic level. At the microscopic level, we basically start explicitly modeling the matrix and the fibers, and then we obtain a response, and then this is homogenized in entire structure. That is the finite element representative volume element method. And in Abacus, we have the mean field homogenization method, which is a semi-analytical solution. This is being preferred because it's better than FERV in terms of computational cost, and it's also accurate. So this is being preferred in this workflow to, well, this allows the users to include also nonlinear behaviors. So for example, using the mean field homogenization method, the user can define the fiber material behavior. In this case, could be elastic. And then for the matrix, the user can define either elastic or elastoplastic, and including viscoelasticity, damage, and failure material models that are coming from Abacus. So basically, most of all the material models available in Abacus can be used in conjunction with this mean field homogenization method. Now, talking more about specifically of the mean field homogenization method. So this basically starts at the element kinetics. So we start including in the material points or integration points the, the, the behavior of the fiber, and then on the material points we define something, some behaviors like the constituent material properties, the volume fraction, aspect ratio of the fiber, and then we perform a volume average operation so that will define the entire behavior of a single element. That's how the mean field homogenization method is working. So on the bottom left side of the slide, for those who are familiar with Abacus keywords, I'm mentioning this because today we're focusing on MODSIM, but if this is needed for a traditional Abacus workflow, these are the keywords that allow for this. So we define the material name as usual, and then we use the keywords to define the MFH formulation. There are formulations such as the one that is very popular, the Mori-Tanaka model. This is where the user defines the formulation to be used. Then we define other aspects such as material that is going to be considered as inclusion, the shape of the material, the orientation, all of these type of properties. So this has access or provide access to all of almost all of the material models available in Abacus. This is provides a very good performance in integration with Abacus. If the information is coming from an external solver, there's a specific script that is provided for free for users to create the necessary files to do the mapping. I'm going to explain that later. But regarding MODSIM, this is an end-to-end solution, and the users don't have to worry about the steps to map the fibers and defining the inclusions, where at least the orientations, the inclusion properties still will be defined. There are some other advanced features, such as defining the concentration tensor for linear elastic materials for the inclusion, that is the fiber. Users could also define the thermal expansion with temperature-dependent coefficients. Viscoelasticity in the time and frequency domain could also be defined, as well as and failure material models. And the output after the simulation can also be requested at the micro level. So that was the regarding the mean field homogenization method. Now regarding the fiber mapping, so the second and fourth order orientation tensor that is being defined by the injection molding solvers. That's how the injection molding solver, not just the injection molding solver in the platform, but any other solvers such as Molfo and Moldex. This is how they define the orientation of a fiber, which is mainly driven by the flow matrix flow direction. So then we get the orientations, and then if we look at the image in the bottom left side, this is the fiber orientation prediction from the injection molding solver. This is the maximum principal tensor for the fibers. Then this is mapped to a structural simulation mesh. In this image, this is just a portion of the entire model. As an example, it doesn't have to be the same mesh. We can only take a portion of the model, and the fibers will be mapped. In this example, we're also mapping a webline. That's also possible. I'm going to talk about this in detail later. And then after doing this mapping, in this example, we are modeling failure for this component using explicit analysis in which we can directly, this kind of behavior cannot be, we cannot get this type of results if we don't include the wet line prediction from the injection molding solver. On the right side is just an example of how we define the fiber reinforcement material property on the platform. There are other material models being enabled here, such as plasticity, ductile damage. It's not being shown here because the list is very large, but also elasticity. And in this screen, we define the formulation that is going to be used for the mean field homogenization. Then the fiber orientation tensor, this is going to be overridden by the fiber direction prediction. And in the last section, we can define the material properties for the inclusion or the fiber. We can see here we have the possibility to define elasticity, expansion, thermal conductivity, the density, and the specific heat properties for the inclusion, that is the fiber. Now, talking about some mapping capabilities. So either in traditional Abacus workflow or in using the MODSIM approach, users can map the spatial distributions. That's what we discussed previously, which is the fiber orientation. But we can also define an initial temperature. This could be useful for considering the thermal expansion of the material during a simulation. We can also take the initial stress, that is the residual stress from the manufacturing process, and some initial field. The wet line mapping, it's part of this capability, the initial field. So as I was saying, we have on the left side here our source fiber orientation data. This is coming from the injection molding simulation. It does, as I said, it doesn't have to be from the native injection molding solver. The source could be from third-party solvers as well. And on the right side, we have the target mesh, which is the structural mesh. And we have what we're looking at is the mapped fiber tensors. And as I was saying, there is a Python script available for free if we need to take fiber orientation data from third-party solvers such as Moldflow. From Moldflow, we can get an XML file, and the script is going to translate the XML file to a SIM format. That's the format that Abacus needs to read to map the fibers and other variables such as temperature and stress. Now, regarding wet lines, so wet lines are formed when two different flow fronts meet. So the default parameter from the injection molding solver is when the solver measures the inclination angle between the two flow fronts. If the angle is less than 135 degrees, the solver will consider this as a wet line. And if it's greater than 135 degrees, then it will not be considered as a wet line. And this is something that we can map from the injection molding simulation. And when we map this, we can use a strength reduction or knockdown factor that's basically affecting the material elastic properties with getting a reduced stiffness. And then what we can see on this XY plot, we can see with the blue line, that is the component stress versus strain behavior when we don't have any wet line considered, and then with the red line we are capturing this response when we include the wet lines. That is applying the knockdown factor to the wet line location. So in the image here we have the equivalent plastic strain output variable from Abacus when we don't have any wet line. And on the right side, we have the behavior. We're capturing the behavior of the wetline in the structural simulation. So the first plot is just the mapped wetline into the structural mesh, and this is the application of the knockdown factor. Then what we are seeing here is the plastic strain output and the material degradation output. And this is an example about how it looks like. So as this is similar to the previous example, right? So we have from the injection molding simulation the injection location, and we predict the flow, and we capture the wetline. And then we map the wetline as a field variable in the structural scenario. So we have here the wetline. And then we perform, in this example, a structural simulation considering the wetline. And we are, having a more realistic behavior because of the wetline influence in the component. And to finalize the fiber reinforced topic, there is also some material calibration capabilities available. There are 3 different modes. Analytical, that's a mode intended for hyperelastic materials. There is a numerical approach that can be used for the elastic fiber reinforcement material behavior, where users can bring their experimental data and provide the initial material coefficients for the matrix and for the inclusion, in this case, the fiber. And what is going to be happening basically is the application, we will go through a optimization process to find the right material coefficients to capture the experimental data behavior. And after the calibration, the application automatically can generate the material card that can be used directly for simulation. So with all that said, let's, I was just focusing on explaining the fiber orientation capabilities in this workflow. But if we talk about, again, the traditional workflow, so we said we have a CAD design, right? And we share the CAD design with the injection molding simulation user to perform the manufacturing simulation process simulation. And then we send the same file to the structural simulation user, or the probably the meshing engineer could also be. And this is a file-based system, right? So we send different, maybe the same model, but different files to each of these users. The injection molding simulation user performs the jobs and obtains the fiber orientation data. And then separately, using another tool, such as could be HyperMesh or ANSA for pre-processing, the fiber orientation data that could come from, we're mentioning here SolidWorks Plastics or MoldFlow or Moldex 3D. That's a different file, and we provide the mesh, and that's a different file. So far we have talked about, almost 8, 9 different tools, right, that could be participating. And now we use different tool to perform the fiber orientation mapping using mean field homogenization workflow and material calibration. So this is just another set of tools to perform the mapping, and then we send the structural mesh result to the structural simulation, and then we obtain responses, and based on the output we iterate, right? So we go back to the design and perform the same workflow again. So as you can imagine, this workflow, it's, the data, it's disconnected between different applications, different systems to share the files, right? It could be email, or it could be a shared folder, or others. And this is considering multiple different tools, and this is a constraint also for, if we want to perform design exploration, this is not making it easy, right? So with the MODSIM approach, what we're looking at is through the platform that it's managing the data. So every user is working with the same data. We're not working anymore with files. Which the plastic part designer creates the part. So the injection molding simulation user can pick the file from the database and perform the simulation, then obtain the fiber orientation data, and that's immediately available for the structural simulation user to do the mapping and perform the simulation. And because of the, the data is connected, so this process can be automatically executed multiple times. So the user spends more time, evaluating results than rebuilding the simulation model, execute the job again, send the new files of the fiber orientation, because in this workflow, the fiber orientation data is directly connected between the injection molding simulation and the structural simulation. So that's, the benefit of using a data-centric approach instead of using files. So as I was saying, this enables design exploration. So what we're looking at here is, we call this environment or this application process composer that basically allows us to define automated workflows. In this case, it's an automated design of experiments where in an automated way, we are changing the injection location and again, automatically doing the the injection molding simulation, and then mapping the fiber orientation to a structural mesh, and then perform the structural simulation automatically. So this way, we spend more time evaluating this type of results instead of manually mapping the fiber orientation. So to summarize, I was describing this workflow, right? We perform the plastic injection simulation user performs the simulation, and then the structural simulation user automatically can extract the fiber orientation without setting up any file. Same thing happens with the weld line. The weld line can be defined as a field variable, and we can consider the weld line influence in the structural behavior. But the same could happen with other workflows, such as, from the injection molding simulation, we can get the process temperatures, and we can map not just the temperature, but also the pressure inside the cavity and the clamp force to a structural model of the entire mold. And we can map the temperatures to obtain thermal stresses, and as well as the clamp force to consider how is this affecting the mold. And we can actually reuse the structural simulation results in a durability simulation. And this is helpful to define, the number, get an estimate of the number of shots when we may need to perform some maintenance to the tool, right? And not only define the temperature as a load for thermal stresses and the clamp force for a structural response, but we can also map the temperatures and as well as the cooling system with the entire mold, and we can actually do CFD simulation to calculate the heat transfer throughout the entire mold. And this also happens using the MODSIM approach. No need to share any files or manually updating files. There is a direct communication between the injection molding simulation and thermal or structural simulation. There is also another interesting workflow that the MODSIM approach allows, which is morphing the geometry And this could be used in two different ways. We can um, morph the geometry for compensation purposes of the cavity. We can, there are specific tools to map the warp results and uh, to perform compensation tasks into the mold cavity, or we can also use the deformed shape of the plastic part to simulate an assembly step, or how is this going to be being assembled. And final step, I mentioned before the automated optimization workflows. So this is how it looks like. This is a process composer application available on the 3DEXPERIENCE platform, where we can basically manipulate different simulations, extract outputs, map the outputs to a specific parameter, and we can start, evaluating these parameters. So in this example, users can define multiple injection locations, and this process can automatically submit all the jobs and do the results analytics, so we can evaluate or investigate the design space and come up with what would be the best number of injection locations, or in the injection location position. All right, thank you everybody for your time today.